So what we're going to do here is use our idea of taking the limit as n approaches infinity of a sum of rectangles under a curve to evaluate this integral that we've been given. So we're told here that the function is e to the x, and we're also told that the beginning of our interval is 1, the end of our interval is 3, and it looks like we don't have a number of rectangles, obviously, so n is approaching infinity. There is no n value because it's approaching infinity. All right, a couple things to take note of here. We've got a change in x that we should calculate. That's calculated by b minus a over n. And so in this case, that's going to be 2 over n. That's an important thing for us to have written down. And then we're going to have the markers on each of our intervals, right? So if it's a right-hand interval, then I'm going to use xi, and that's going to be calculated by a plus I times delta x. And so the beginning of our interval is 1, and that's I times 2 over n. So this is going to equal 1 plus 2i over n. And so that's going to be our value that we're going to be evaluating our function for. So we end up with this integral from 1 to 3 of e to the x dx being the same exact thing as the limit as n approaches infinity of the sum of rectangles from our first through our nth of f of xi times delta x, and this is where I can replace that function xi with the value that we've just calculated. All right, we've set this thing up. Now remember, in the last video we discussed the fact that with respect to this sum, 2 over n is actually a constant. It's not a variable because we're plugging in values to the sum where we see I. So this can be removed. It can't be removed from the limit, but we can remove it from the sum. So I'm still taking the limit as n approaches infinity, but now I'm going to remove that 2 over n from the sum and multiply it by the sum that we have left, which is f of 1 plus 2 to the I. This would be a good time to actually evaluate f of 1 plus 2 to the I. If this is f of x, then that just means e to the power of 1 plus 2i over n. And that's the exponent there. And so we were just told to set up an expression. This would be that expression. But now that we've set it up as an expression, we might be able to use some of our sum rules to help simplify that. But this is the expression that we would be left with. And it's good to get in the habit of getting to that point with different functions relatively quickly. A couple more examples that are a little different from previous examples. Let's evaluate these by interpreting them in terms of area. And the reason it's written like that is what we're not going to do is approximate using rectangles here. We're going to recognize that with these, I could just calculate the exact area pretty easily with the way that these functions are written out. So if I take a look at this first function, our function is the square root of 1 minus x squared. And what we should recognize is that if y equals 1 minus x squared, the square root of all that, that is the same as y squared equals 1 minus x squared, which is the same as x squared plus y squared equals 1. This is the equation of a circle with a center at 0, 0 and a radius of 1. Okay, so with that in mind, we know what this is going to look like. This is the positive side of the circle because this does not say plus or minus, right? This is only the positive values of that circle. So if I sketch a little graph of what it is I'm looking at here, I'm sorry for the squiggly line there, but that is our x-axis. What we've got is the top half of a circle where that's 1 and that's negative 1, and this is also 1 on the y-axis. Radius of 1, centered at 0, 0. But remember, we're taking the integral from 0 to 1, so we're actually not even including any of this. It's just this part of that circle, which amounts to a quarter of that circle. So sure, I could approximate this with Riemann sums, and I could take the limit of the number of rectangles as n approaches infinity. But I think what would be more efficient here is if we recognize that this is just a quarter of the area of a circle that has a radius of 1, which is a pretty simple thing to calculate. So what I could say is that this area is equal to 1/4 pi r squared. That's just the formula for the area of a circle. And the radius of this circle is 1. So pi over 4. And we could have calculated that using our limits and using Riemann sums, but just an example of a area that would be easier to calculate using logic and area formulas that we're aware of. Another example of that here is a linear function, and linear functions are pretty easy to calculate the area under a curve because we're going to use a different shape. If I take a look at what this function looks like, and again I'm going from 0 to 3 on the x-axis, this is a line with a slope of 1 and a y-intercept of -1. So this is the y-intercept of our function here, and it goes up 1 and over 1. So at 1, we would have another point. I would have another point at 2, 1, and then we'd have another point at 3, 2. And this is what that function would look like. It's just a straight line, but we are calculating the area under the curve from 0 to 3. So this is where we're calculating. So that means we have this area here, and we have this area here that we're calculating, and we're going to want net area. So we're going to want to take the area of this negative section away from the area of this positive section. And to calculate that area, you can see we've just got two triangles here. So we're going to want to use the area of a triangle to actually make this calculation. If I take the area of the first triangle, that's going to be 1/2 of the base times the height of that triangle. The base of that triangle is 1, the height of that triangle is 1, so that's 1/2. And if I take the area of that second triangle, that's 1/2 of the base, which is 2, times the height, which is 2. And that's half of 4, which is 2. So I could say, therefore, the integral of x minus 1 over the interval from 0 to 3 is the same thing as 2 minus 1, because we're talking net area here, right? This is all positive area, and this here is all negative area. So I want to subtract my positive area minus my negative area. And that shouldn't say 1, that should say 1/2, because that's the value we calculated there. And so that would be 1.5. Another example where we could have used rectangles, we could have taken the limit of the amount of rectangles as that number approaches infinity, but if we use some logic and take a step back and realize that these are shapes that we know how to calculate the area of, we could maybe save ourselves some time.